Assalamualaikum and good morning, everyone. Okay, so today we are going to learn new lecture. So today is lecture 4B regarding the steady state error for unity feedback system. So in today's lecture, we are going to look at how we can determine steady state error, and then we are going to be introduced to new terms like unity feedback system. So what is unity feedback system? And later on, maybe after this lecture, you will encounter a lot of terms. We are going to encounter a lot of usage of this term, unity feedback system. So after completing this lecture, you will be able to determine the steady state error for a unity feedback system due to step, ramp, and parabolic input, and then determine the static error constant for unity feedback system, and lastly determine steady state error performance specification for unity feedback system. So let's review on the different types of input that you have learned, I think in lectures before midterm break. So there are three types of input. So we have step input. So step input is basically a constant value, but a unit step input, we give the value of the constant equals 1. And then in Laplace or in frequency response, the input will be 1 over S. And then we have ramp input. So for a unit ramp input, it becomes T, okay? Just a value T. And then in frequency, it will be 1 over S squared. And then for parabolic input or unit parabolic input, it will be 1/2 T squared. And then in frequency domain, it will be 1 over S cubed. Okay, so from now on, we are going to use these three types of input: step, ramp, and parabolic input. So there are a lot of other types of input, but these three inputs are the most, I would say, the most basic, okay, the simplest inputs that we can use to analyze a system. Okay, now let's look at steady state error. So steady state error is the difference between the input and output for a prescribed test input as the time approaches infinity. And then the steady state error analysis is only applicable when the system is stable. So if your system is unstable, then it will have no steady state error because it will not reach steady state value. So we cannot analyze steady state error for unstable system. So please remember this. If you want to analyze steady state error for a system, you must make sure that the system is stable. Okay. If it's not stable, then you cannot analyze the steady state error. So there are a lot of sources of error. So number one is when you use nonlinear elements. So nonlinear elements like spring and dampers. So we learned that a linear spring maybe has a Hooke's law relationship. So force equals K times X. So maybe nonlinear, maybe it will be like K times X squared, for example. So the relationship is nonlinear. So when you have nonlinear springs or damper, then there will be error, or the steady state error will be bigger. And then if you have gearing, so the contact between two gears will produce friction. So the friction will produce errors as well. And then the different types of system configuration also can produce error. So we have unity configuration, unity feedback, and also non-unity feedback. So different types of configuration will produce different types of error. And lastly is the different types of input that you use will also in this topic, how different types of input can produce different values of error. And then we focus on the unity feedback system. So let's look at how to evaluate steady state error for a step input. So if you have a step input and then you plot the time response, then you will see that the top, the graph output 1 here basically reach the steady state value similar to the input value. While for output number 2, it also reaches steady state value, but it doesn't reach the original input value. So the difference between the input and output number 2 here is the steady state error for step input. Okay. And then if you have a ramp input, then the time response will have a different different shape, okay? Different kind of shape compared to step input. So here, if you have a ramp input, then the method to calculate the error is slightly different. Okay. But we won't calculate from graph. We will use a formula to calculate the steady state error. So to calculate the steady state error, we have to introduce the final value theorem. Okay, so we're using the final value theorem, we can calculate the steady state error. So the steady state error, E infinity, equals the limit when time approaches infinity for an error E of time t, for error function E times E of t. Also, if you convert this into frequency using Laplace transform, it is the limit when s approaching 0 for s times e function of s. Okay, so let's look at an example for unity feedback system. Okay, so firstly, let me explain what is unity feedback system. So a unity feedback system is this block. Okay, so this block diagram here. If you have unity feedback system, then the feedback transfer function here is equals 1. Okay, while it only has a forward transfer function gs. So a unity feedback system, when you are given a question, let's say in exam, to simplify a unity feedback system, then you have to know that it is this system. Okay, it has forward transfer function gs, so forward transfer function, and then a unity feedback transfer function equals 1. Okay, so the transfer function for feedback equals 1. So we can simplify this. So you can calculate the error E here equals R minus C. So this derivation is just for you to understand. Okay, so E equals R minus C, and then C equals E times G, and then you can substitute. You can find E equals R over 1 plus G. So here the error depends on the input R. So this is input, and depends on this forward transfer function. So it only depends on these two, input and the forward transfer function. So using the final value theorem that I've shown earlier, so the error, the steady state error, is basically the limit when s approaching 0 for s of e, s times e equals the limit of s approaching 0 for this s r over 1 plus g. So this is how you can find the steady state error for a unity feedback system. So let's look at how to use that formula. If you have a step input, so let's say if you have a step input, so to find the steady state error using this formula, and then you just substitute RS with step input. So step input just now is in time domain is equals 1, and in frequency it equals 1 over S. So you just substitute R equals 1 over S, and then you get 1 over 1 plus GS, and then because only GS that is dependent on S, so the limit is only for GS. Okay. So in order for this system to have zero error or zero steady state error, or we want the E infinity equals 0. So the only way this can happen is when the limit when S approaching 0 for G is equals infinity. So what happens is that when this the denominator becomes infinity, then everything becomes 0. So for this system to have error, then this limit must be infinity. So let's say if your GS, your transfer function GS equals S plus Z1. So Z1, Z2 here is the zeros. And then P1 and P2 are the poles. So divided by S power of N times S plus P1 times S plus P2 and so on. So here, for this limit to be infinity, then N must be bigger than 1. Okay, must be bigger or equals 1. So in order to have zero steady state error, N must be equal or greater than 1. There must exist at least one pole at the origin. So if we have N equals 0, if we use N equals 0, then we have the error limit of S approaching 0 for GS equals Z1, Z2, Z3, and so on, divided by P1, P2, P3, and so on. So here, if we use N equals 0, then the error will not become 0. Okay, there will be a steady state error. Okay, so for N equals 0, then the system has an error. If N equals 1 or more than 1, then the system will have zero steady state error. Okay, so that's for step input. Now let's look at for ramp input. Okay, so similar analysis. So for ramp input, in time domain, it is just T, and in frequency domain, it's 1 over S squared. So you substitute 1 over S squared, so you end up with this 1 over limit of limit when S approaching 0 for S times G. So in order to have zero steady state error, okay, then this limit must be infinity. And then similarly, if we use the same G as previously, so for this limit to be infinity, then N must be bigger than 2, okay, bigger or equals 2. So in order to have zero steady state error for ramp input, then N must be equal or greater than 2. So there must be at least 2 poles at the origin. So if we have, if we use N equals 1, then the steady state error will be this one, Z1, Z2 times Z3 and so on, over P1 times P2 times P3 and so on. Okay, so there is an error, finite steady state error. And if we use N equals 0, So we have the limit of this limit equals 0. And when this limit equals 0, then the steady state error will be infinity. Okay. So why infinity? Because from here, if this limit equals 0, then 1 over 0 is equals infinity. Okay. So if we use n equals 1, then we have a finite steady state error. And if we use n equals 0, then we have infinity steady state error. Okay, so that's for ramp input. Now let's look for parabolic input. So parabolic input, we have a half t squared, and in frequency domain, it's 1 over s cubed. So similarly, in order to have using the same G, then in order to have zero steady state error, then n must be equal or greater than 3. So you must have at least 3 poles at the origin. And then if we use n equals 2, then we have finite error. If we use n equals 1 or less, then we have infinite error. Okay, you can try this, try to prove this by yourself, okay? So from this analysis, we can determine something we call static error constant, okay? So just now we determine the steady state error. So in order to determine steady state error, we basically need to determine this limit, okay? So this limit is known as the static error constant. So for step input, the static error constant is known as the position error constant, Kp, equals the limit of G when S approaching 0. And then for ramp input, it is known as the velocity error constant, or Kv. It is the limit of S times G when S approaching 0. And lastly, for parabolic input, we call the static error constant as acceleration error constant. Ka equals the limit of S squared times G when S approaching 0. So these three limit or constant here, you must determine first in order to determine the steady state error. And we can summarize this in a table, okay? So the static error constant can assume three values, so either 0, finite constant, or infinity. So the value of steady state error decreases as the value of static error constant increases. So what you need to remember is that for step input, you have to use Kp, and then for ramp input, it's Kv, and for parabolic, it's Ka. Okay, so let's move on. Okay, so now let's look at the system types. Okay, so just now I explained to you about this transfer function GS can be equal this S plus Z1 times S plus Z2 over S times S power of n times S plus P1 times S plus P2 and so on. So we know that when we use different value of n, then we get different types of error, either zero error, zero steady state error, finite steady state error, or infinite steady state error. So here, the n here is known as the system type. Okay. So if we have n equals 0, then the system is type 0. If we have n equals 1, then the system is type 1. N equals 2, then the system is type 2, and so on. Okay. So n here determine the system types. So if we have type 0 system, okay, so s power of 0 equals 1. So here is an example of type 0 system. So let's say you are asked to evaluate the steady state error constant and the steady state error for this type 0 system for step, ramp, and parabolic input. So you can calculate Kp, all the static error constants, Kp, and then calculate the steady state error, and then calculate Kv, and then calculate the steady state error, and then calculate Ka, and calculate the steady state error. So we can see that here, when you have a parabolic step input, then the steady state error is finite. Okay. While if you have ramp and parabolic input, then the steady state error are infinity. Now let's look for type 1 system. So type 1, you have s power of 1. So here you have s power of 1 here. So similarly, evaluate the steady state error constant and steady state error. So Kp equals infinity. So steady state error is 0. Kv equals some value. So steady state error is finite. And lastly, Ka equals 0 and steady state error is infinity. And lastly, for type 2, so type 2 you have s power of 2. So similarly, Kp equals infinity, the steady state error is 0, Kv equals infinity, so the steady state error also 0, and Ka equals some value, so the steady state error is finite. Okay? You have value for steady state error. So from here, we can summarize all of this again. So if you have type 0 system, then only step input has an error. It will produce error if you use a step input for a type 0 system. And if you use ramp or parabolic input for type 0 system, you will have infinity steady state error, or the system is unstable. Okay? And then for type 1, if you use step input, then the error is 0. For ramp input, you have some error, finite error. And for parabolic input, you have infinity error. And then lastly, for type 2, if you use step and ramp input, then the error is 0. And for parabolic input, you have finite steady state error. Okay, so you just need to remember this table. Okay, for if let's say question coming out in quiz in final exam, so just remember this table. Okay, any question before we go to some example?
No, Ruben.
Okay, so for this topic, basically you just need to remember this formula lah. Okay, this slide, remember this slide. And then just looking at this trans function and determine the type, you know that what kind of input to use in order to produce zero steady state error, or if you want to produce a small amount of error in your system, or you can avoid producing infinity error. Okay, so here you know that for type 0, you can use step input to produce a bit of error. If you use ramp or parabolic input, then the error will be very large, okay, infinity. So for type 1, you can use step input. so that the error becomes 0. So for type 2 as well, you can use step or ramp input to produce 0 error. Okay, so you know from here how to avoid infinity error. Okay, just based on the type of system and the type of input that you want to use. Okay, so now let's look at an example. So let's say if you have this transfer function. So let's say this is a unity feedback system. Okay, so let's say this is a unity feedback system. So the question asks you to evaluate the steady state error constants and the steady state error for step, ramp, and parabolic input. So if you look here, then you know that S is power of 0. Okay, so here S power of 0 here, so equals 1. So you know already this is type 0. So type 0, you will expect to have error for step input and infinity error for ramp and parabolic input. But let's look at how to do the analysis here. So firstly, you need to make sure that the system is stable. Okay, so only stable system has a steady state error. For unstable system, will have no steady state error. So you must check first whether the system is stable or not. So this is just dia punya formality. Okay? Formality, you need to check the stability. So you have to find the closed loop transfer function. So it's a unity feedback. So G over 1 plus G, and substitute everything. And then use the denominator to generate the Rapp-Hurwitz table. Okay, so you can generate the Rapp-Hurwitz table. And then look at the first column. So in the first column, there is no sign changes, all positive. So meaning that all poles are located in left half plane. So the system is stable. So we know that the system is stable, then we can determine the type of the system. So it's a type 0. And then from the table, for type 0, we know that Kp, you can calculate Kp. So it's 1 to 7 equals 1 to 7. And then the steady state error for step input is 7.8 times 10 power of minus 3. And then for the other input, Kv and Ka equals 0. So the error is infinity. Okay, so that's it. Okay, simple je. So now let's look at another example. So let's say you are given a specification. So let's say you are given a specification to maybe develop a system that has KV equals 1000. So what can we derive about the system? So the system is stable because it has a static constant, okay, static error constant. And then the system is type 1 if we want the steady state error equals 0, equal something, lupa dah table tadi. Okay, type 1 because if we want it to have a steady state error, then it must be 1 over kV. So if you use type 0 for a kV value, then for type 0, there will be no kV. And then for type 2, kV equals infinity. So if you are given a kV value, then you know that the system must be type 1. Okay. So it's a type 1 system. And then a ramp input can be used to produce a steady state error. If we use step input, then there is no steady state error. Then the steady state error is 1 over kV if we use a ramp input. So you cannot use parabolic input for type 1 because it will produce infinity error. If you use step input, okay, yes, you can, but the error will be 0. Okay. So later, maybe after maybe in the following week, we will see the advantages of having a zero steady state error system or a system with a slight error. Okay, there are some advantages. Okay, sometimes if we use a zero steady state error system, then we have drawbacks in other things like it will produce overshoot, for example, or rippling. If we use some slight steady state error, then there will be no overshoot. Okay, so there are pros and cons of using zero steady state error system or system with some steady state error. And then example number 3. So let's say you are given this unity feedback system with forward transfer function. So you want to find the range of k so that the steady state error is about 10%, is 10%. So we know that this is a type 1 system. So because s power of 1. So for a type 1 system, we have kp equals infinity, kv is a constant, and ka is 0. And we want the system to have a steady state error 10%. So for a steady state error 10%, then we must have some static error constant, because if we use kp, then the steady state error is 0, and then ka, the steady state error is infinity. So only kv will produce some steady state error. So now we can determine kv from this 10% here. Okay, so for step input, the steady state error is 0. For ramp input, the steady state error is 1 over kV. For parabolic input, the steady state error is infinity. So only ramp input will produce some error. So since the steady state is specified as 10%, then it must be using ramp input. Okay. So we can determine kV. So the steady state error is 10%, 0.1. So 0.1 equals 1 over kV. So kV equals 10. So we got kV equals 10. So kV equals 10 equals the limit of s times g when s approaching 0. So you substitute g with this transfer function. And then use s approaching 0, the limit. So you get this k times 5 over 6 times 7 times 8. So using kV equals 10, so you can get k equals 672. Okay, so this is how you find k. And then after you find k, then you can check whether the system is stable or not. Okay, it is stable because you are given already, but it's always good to check using Rath-Hurwitz criteria whether the system is stable or not. If you are given k equals 672.
Betul.
Yep.
Find k so that the steady state error is 10% tu, itu question ke ataupun
Question je.
Oh, question ingat. Oh, bukan notes lah. Okay.
Bukan.
Find k that steady state error is 10% lah. Okay. Okay.
Okay, so let's look at tutorial. Okay. So dah habis lecture. So let's look at tutorial. So tutorial 9 is about steady state error. Okay, so let's look at the first question. So determine the steady state error under the step input 5 UT, ramp input 5t UT, and parabolic input 5t squared UT for the system below. Okay, so firstly, you need to determine the type of system. So here, the type of system is S power of 1. So it's a type 1 because n equals 1. Okay. So for n equals 1, we can refer back to the lecture notes. Saya pun tak ingat, so kena refer balik. So for type 1, we will only have steady state error for a ramp input. Okay. For ramp input, we have steady state error. For step input and for parabolic input, we have 0 steady state error and infinity steady state error. So here for this question, if we use 5 UT, we get 0 steady state error. If we use 5t squared UT, we have infinity steady state error. So now we only need to determine the steady state error when we use 5t UT. Okay, so firstly, if we have the input equals 5t UT, then in frequency, it will be 5 over S squared. Okay, so we need to determine KV first. So let's go back to lecture notes. So KV is basically determined using this formula. Okay, S times E, or limit when S approaching 0, S times R over 1 plus G. Okay, we can determine KV, but since the input is not unit step, unit ramp, it's a 5 ramp input. Okay, so we can determine the steady state error from this formula straight away. So steady state error is the limit lupa lah 1 plus G. Then you just substitute G and R. Macam salah. So you will end up with oh kenapa salah? Sekejap. Type 0 lah. Okay, salah type. Betul lah. So it's a type 0, sorry. Type 0.
Macam mana
So,
doktor boleh nak tahu dia type 0 doktor ataupun type 1?
kat sini tadi, sorry. S power of 0 kat sini. So if you look at the transfer function, GS here,
yang depan tu,
and
okay.
dia type 0. So silap lah. Ni
Formula
silap.
dia.
Okay. Betul.
Yes.
So
And
for type 0, okay, so panjang-panjang bebel tadi is a type 0. So 5 UT RS equals 5 over S. So steady state error for RAM input is infinity. For parabolic input is also infinity. So similar steady state error for step input. So you get limit S approaching 0, SR over 1 plus GS. And then substitute everything. So you get 5 over S over 1 plus 120 S plus 2 S plus 3 times S plus 4, and then just substitute S equals 0. So you get 5 over 1 plus 120 times 2 over 3 times 4. Okay, so you can calculate by calculator. So you get steady state error for step input equals 5 over 21. Okay, that's it for this. So you need to determine the type of system, and then from there you know that which input will produce steady state error and which input will produce zero error and infinity error. Okay, now let's look at tutorial question number 2. So question number 2, find the gain K so that the steady state error of a unity feedback system with forward transfer function below is 10% and then 1%. So there are two questions here. So first, the type is type 0. So for a type 0, then we refer the table again. So for a type 0, to produce steady state error, we can only apply step input. Okay, so if you apply ramp and parabolic input, then the error will be infinity. So you need to apply step input. Okay, so only step input. Steady state error. And then from there, you can use, you can find KP. So So Kp is by using this formula, steady state error is 1 over 1 plus Kp. Okay, so let's say your steady state error is 10%, so 0.1. So steady state error equals 0.1. And then for step input, it's 1 over 1 plus Kp. And then from here, you can determine Kp equals 1 over 0.1 minus 1. So Kp equals 9. Then from here, you can determine K. So so again, tengok lecture note, lupa. So using the limit, so Kp equals the limit. So for Kp, it's a slightly different. So Kp equals limit s approaching 0 for G. So Kp equals limit s approaching 0 for Gs equals 9. And then this is your G. Then substitute in here. So you get K times 12 over 14 times 18 equals 9. So you can find K. So K equals 189. Then you get your K. So your GS will be 189 times S plus 12 over S plus 14 times S plus 18. And then you can check whether the system is stable or not. So just formality. So to check, you need to find the closed loop transfer function. So it's a unity feedback system. So unity feedback system, closed loop transfer function is G over 1 plus G. So you end up with and then expand the denominator. Or just take the denominator. Dia dah lagging dah benda ni. So S squared Okay, then simplify dulu. Then you can do Rutherford's criteria table. Okay, then determinant. So here you get 630. Okay, so if you look at the first column, there is no sign changes, then the system is stable if you use k equals 189. Okay, so for 1%, you can try by yourself, similar step, but the value will be different. So the stability might be affected. Okay, so you can check later whether the system is stable or not by using Rutherford's criteria, or just simply finding the poles. Okay? You can find poles if the poles are if there is at least one pole on the right hand side, then the system is unstable. Okay, so that's it for steady state error. Any question before we end this lecture?
Masih lagi memahami. Tapi terima kasih Dr.
Okay, tak apa. Take time sikit. Okay, so if you have no question, then that's it for this lecture on steady state error. And then we will meet again next Wednesday. Okay, Monday is holiday. So on Wednesday, we are going to learn new topic. So in this new topic, root lockers. So in root lockers, I hope you by now you understand how to determine, how to perform the route of table, how to generate the route of table, how to determine poles and zeros, because we are going to use this a lot of time, and maybe during the calculation you might get lost. Okay, so I hope you can revise by yourself how to do the route of table, how to determine the poles and zeros, and then just refresh what have you learned, okay, what you have learned until today. Okay, so if there is no more question, we end the session for today. So thank you very much. Assalamualaikum and goodbye.
Thank you Dr.
Thank you, Doctor.
Thank you.
Salam.
Thank you, Doctor.
Thank you very much.
Thank you, Doctor.
Thank you very much.